Our starting point is a normal form game with 2 players. Initially, we consider the most simple case with 2 actions per player. So we have 2 players called 1 and 2, 2 actions for player 1, namely A1 and A2, 2 actions for player 2, namely A3 and A4. We introduce the leader-follower paradigm. We assume that player 1 plays as the leader, while player 2 plays as the follower. This modifies the structure of the game. In principle, a leader-follower paradigm can be applied to any game, including those in extensive form. The game to which we apply the leader-follower game is called the underlying game. Now we analyze the leader-follower paradigm. First, the leader announces her strategy. Such a strategy may be mixed. The announce is basically a commitment. That is, the leader is committing to play the announced strategy. Second, the follower observes the announcement of the leader. Third, on the basis of the observation, the follower decides her strategy. That is basically a best response to the strategy of the leader. Fourth, the players play simultaneously. This is because the underlying game is a normal form game. Otherwise, if the underlying game is in extensive form, the players play according to the sequential structure of the game. For a better clarity, we report an example. Suppose that the leader announces the strategy reported in the slide. That is, to play A1 with 1/3 and A2 with 2/3. Such a strategy is not optimal, but it is useful for our example. The follower observes the strategy of the leader. The follower computes the expected utility she will gain when playing A3 or A4. Action A3 gives an expected utility of 1, whereas action A4 gives an expected utility of 3. Thus, the unique best response of the follower is A4. Therefore, the strategy of the follower is exactly to play A4. Finally, the players draw their actions from the strategies. For instance, A1 for player 1 and A4 for player 2. Our problem is that one of finding the best strategy of the leader, leading to the so-called leader-follower equilibrium or Stackelberg equilibrium. We consider the same game as before. We need, as usual, to study the behavior of a player as the opponent changes her strategy. In particular, we need to study the behavior of the follower as the leader changes her strategy. So we need to focus on the simplex of the leader. The simplex of the leader is a line representing the probability with which action A1 is played. Specifically, the right extreme of the simplex corresponds to the playing action A1 with probability 1, while the left extreme of the simplex corresponds to playing action A2 with probability 1. When action A1 is played with a probability of at least 2/3, the best response of the follower is A3. Whereas, for every other strategy, the best response of the follower is A4. Focus on the expected utility function of the leader player as her strategy changes. The goal of the leader is to maximize her expected utility. The crucial point is where is the maximum. Indeed, the maximum is when action A1 is played with a probability of 2/3, but For such a value, the follower is indifferent between actions A3 and A4. This means that the follower has several ties, and the tie-breaking rule is crucial. If the follower ties are broken in favor of the leader, then the maximum is exactly at 2/3. Otherwise, the maximum does not exist, being 2/3 plus epsilon, where epsilon is an arbitrarily small, strictly positive value. We analyze the properties of the Stackelberg equilibrium. First, an equilibrium always exists when ties are broken in favor of the leader. Second, an equilibrium may not exist when ties are not broken in favor of the leader. More precisely, the optimization problem always admits a supremum, but it may not admit a maximum. Third, under some conditions, committing to a strategy never hurts the leader. These conditions are: there is a single leader and a single follower, and the ties of the follower are broken in favor to the leader. Equivalently, under those conditions, the Stackelberg equilibrium provides the leader a utility that is never smaller than the utility of the Nash equilibrium that is the best for the leader. In this example, we can observe the relationship between the equilibria. Assume that player 1 has no information on player 2, and thus she plays her max-min strategy to maximize her utility in the worst case. This corresponds to play action A1, and her utility is 3. Furthermore, this is the worst case for player 1. Assume that player 1 knows the utility of player 2. This game admits only one Nash equilibrium, in which player 1 plays action A1 with a probability of 2/3. The expected utility of player 1 is 3.5, larger, obviously, than the expected utility of that player at the max-min strategy. Assume that player 1 has the power to play as a leader, thus announcing her strategy. In this case, the best strategy to commit to is the same she plays at the Nash equilibrium, but the expected utility is much larger, being 4.3. So player 1 can get more in terms of expected utility as she gets information on the opponent and she gets the possibility to play as a leader. Now the goal is to show that the Stackelberg equilibrium with optimistic tie-breaking rule that is in favor of the leader may be arbitrarily better than the best Nash equilibrium for the leader. Consider this game. The game admits only one pure strategy in Nash equilibrium, that is action A2 for player 1 and action A4 for player 2. The utility of player 1 is 1. Now we focus on the Stackelberg equilibrium. It prescribes that player 1, that is the leader, plays 1/2 on action A1 and on action A2, while player 2, that is the follower, plays action A3. The leader gets k plus 1 divided by 2, that is arbitrarily larger than the value she gets at the Nash equilibrium. Now we study the optimization problem to find a Stackelberg equilibrium with the follower's optimistic tie-breaking. This optimization problem is a bi-level optimization problem. This in green is the first level optimization problem. Here the objective function is the expected utility of the leader player. The constraints are that the leader strategy is well defined. In red, we have the second level optimization problem. The objective function is the utility function of the follower. The constraints are that the follower strategy is well defined. The connection between the first and the second levels is that the variable sf star of the first optimization level is an optimal solution of the second level optimization given the strategy SL, that is the strategy of the leader. In order to solve this optimization problem, we need to cast it as an optimization problem with a single max or min operator, since we cannot solve it if we keep it as a bi-level optimization problem. A very simple way to solve it is the following. This approach is based on multiple linear programs. At first, we enumerate all the actions of the follower, and for each action of the follower, we find the leader strategy that maximizes the leader utility under the constraints that the given action of the follower is a best response. This can be done by means of a linear program. The objective function is the expected utility of the leader when the follower action is fixed. The constraints are that the leader strategy is well defined and the given action of the follower is a best response. Then, we return the action of the follower such that the expected utility of the leader is maximized among all the follower's actions. Consider this simple example. Given action A3, we find the best strategy of the leader subject to this action is a follower best response. The maximum utility for the leader is 13/3. Given action A4, we find the best strategy of the leader subject to this action is a follower best response. The maximum utility of the leader is 8/3. The maximum of the leader utility is for the action A3 of the follower, and it is 13/3. We focus on a simple variation in which the follower may be of multiple types in the Bayesian sense. That is, the leader knows a probability distribution over the possible types of the follower. This scenario is interesting in many practical real-world applications. Notice that also the reverse is interesting, as well as the scenario in which the uncertainty is both on the leader and on the follower. However, we will not deal this case. We can adopt a multi-LP approach as in the non-Bayesian case. The extension of the previous result to the Bayesian case is straightforward. We enumerate all the possible profiles of actions of the types of the follower. For every profile, we find the best strategy of the leader maximizing her expected utility, subject to the constraint that every action in the given profile of actions of the follower's type is a best response for the corresponding type. This can be done by means of a linear program that easily extends the linear program for the case without types. The only difference is that the utility of the leader is in expectation with respect to the probability distribution over the follower types, and the best response constraints of the follower are replicated for every follower type. Finally, we return the action profile maximizing the utility of the leader. Notice that the number of action profiles rises exponentially in the number of types. So we should ask whether the complexity in this case is hard or not. Specifically, we have that in the case without types, the problem can be solved in polynomial time in the number of actions of the players. In the Bayesian case, instead, the problem is NP-hard, and in particular, it requires exponential time in the number of types of the follower.